Okay, so carbon, right, guys, remember had the up down here, and then had the up down here, and then it was an up and then an up. So we want to represent this using this term called electron configurations, which is a way to represent our electrons inside of an atom. So carbon, because it has 2 electrons in the 1s orbitals, we are going to say that it has 1s2, and then because it has 2 electrons here in the 2s, it has 2s2, and over here you have 2 more electrons in the 2p's, so you're going to do a 2p2. Now again, notice there's a px, py, pz. I won't worry about those. I just care about the fact that there's 2 p's. The x, y, and z are just there to help you remember that these are degenerate orbitals, and there are 3 of them in the 2 p's. Sulfur again is kind of a continuation here, so let's go and fill in the rest of these. So I know these will get paired up, so that's up, down, up, down. This is an up and then a down, and then this one right here I believe is an up and then an up as well. Actually, no, I take that back. It's up, 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 and then down. So following the same pattern, wherever you have electrons, you want to represent that by this. So you're going to make it 1s2, 2s2, 2p, and then all of them are there, so that's 6 electrons, 2p6, 3s2, and then 3p, so that's 4. I apologize for the continuation of terrible handwriting here using my mouse at home. And then you have iron right here. Again, that eventually fills all the way up to 3d, and I know everything up here is filled. It's going to look like this, and so to write it out, I'm not going to write it out for the sake of your vision, but your answer here for iron should be 1s2, 2s2, 2p6, 3s2, 3p6, don't forget the 4s2, and then 3d6. Okay, so there you go. Now, this pattern here goes on, and it's it seems like a very difficult, almost arbitrary pattern here, but it's actually something called the diagonal rule, which sort of shows you the pattern without actually having to look at that diagram we just saw a second ago. So, again, this is called the diagonal rule, which is essentially the Aufbau rule. So the Aufbau rule, if you remember, is the building up from the bottom to the top. But in this case, remember, actually, it's about the energy instead of the energy level. So we're not going by floors. Now, this right here is sort of a representation of what exists. Well, the first floor has S, the second floor has S and P, the third floor has S, P, and D, fourth floor is S, P, D, and F. According to the one that we saw, the dorm analogy, it goes across, and it goes across, and it fills up this floor, and then this floor, and then this floor, so on and so forth. But in reality, we do it by increasing energy, which actually follows this pattern more so on the right, this little diagram, more so than what you see going from floor to floor. Now this diagonal rule, if you kind of notice, it goes from the bottom right to the top left, and it goes 1s, 2s, and then you continue to follow the little arrows. So once you're done with the arrow, come back around and start the next arrow, 2p, 3s. After this arrow, you come back around and go to the next arrow, 3p, 4s, and after the 4s, you come back around to 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. And again, that's what you'll see over here. So if you follow along with the diagonal rule, it is the 1s, the 2s, the 2p, the 3s, the 3p, the 4s, the 3d, then the 4p, 5s, 4D, so on and so forth. Now, again, this goes on for infinity, so you can keep this trend going so long as you want. Now, it'd be a good idea for you to go ahead and know the diagonal rule pretty well. Some of you probably know the trick I'm about to show you, so you don't have to necessarily memorize it. And in fact, it's already embedded elsewhere. But you will probably never really be given this on a test or a quiz. You'll probably never be given this either. So one of the difficult and sort of annoying things is how to be able to know how to do this without actually being given these, and that's where you sort of have to apply it. But we'll come back to that in just a moment. First of all, I want you to try fluorine and krypton. I'm going to pause for just a moment, or you can pause for just a moment here and see if you can figure it out on your own, and then we'll go ahead and talk about the answers. Okay, so fluorine right here starts off as 1s, 2s, 2p, 3s, and so on and so forth. But if you look at the fluorine's number of electrons, it only has 9. So again, according to the diagonal rule, it's going to be 1s2, 2s2, and then 2p5. Right, because all 9 then get assigned once you're in the 2p. Remember that the s's, all of them can hold a maximum of 2, so once you've got your 2, you're done, move on to the next one. And then p's, once you've hit your 6 maximum, then you're done, move on to the next one. But in this case, we stop at 5, so 2p isn't quite filled. Krypton, however, Krypton has a lot more electrons. It has 36, in fact. So Krypton will end up having your electron configuration to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And then you would stop there, right? Because remember that each of these d's can hold a maximum of 10, p's can hold a maximum of 6, and then s can hold 2. So there you go. Now, how to actually use these according to the diagonal rule? Well, the periodic table already has it more or less embedded, and this is where it's really nice. So what I kind of want you to do is sort of do a bunch of electron configurations quickly. Now, of course, that's easier said than done for some of us, but really it starts off like this. I want you to start off just by identifying the last electron configuration term for these blank elements. Right, so for example, hydrogen is right here. Hydrogen is going to end in 1s1. I think that's fairly intuitive. Over here, helium has 2 electrons, so it's going to end in 1s2. The next 2 elements, right, lithium and beryllium. Lithium right here has 3 electrons, and its last electron is going to be 2s1. Now, this doesn't mean that it only has a 2s1. It means that it has 2 electrons in the 1s's, and also 1 more for the 2s. Then you also have 2s2 for beryllium. Again, this is just the last term. Over here, it's going to be a similar pattern. You're going to have a 2p1 right here, 2p2, 2p3, 2p4, 2p5, and then 2p6. All right, the fact that it ends at 6 is not a coincidence. Now, like I said, this should actually follow the diagonal rule exactly. Well, let's see what happens here. So the first term of our diagonal rule is 1s's, meaning we're going to fill in our 1s electrons first, and that's exactly what we've done right here with hydrogen and helium. Lithium, beryllium, they're actually the next up. So after 2 electrons have been filled, you're going to go ahead and move them into the s orbitals, which is going to be lithium and beryllium. That's why you see the s1 and s2 right here. Well, okay, so that's 4 electrons. What about my 5th electron? Well, these again are filled. I can't put any more in these s's, so I have to move on to the p orbitals, where again I notice that my last one right here is going to be 2p1, then 2p2, 2p3, 2p4, 2p5, 2p6. So once the 2p's are done, then I move on to the 3s, which again can hold 2. Then next is my 3p, which is all of these right here. Now notice so far, how are you going to know which one's which, or where they are? Well, all these so far that we've done all end in s's. Notice that this right here is helium. Technically, should also be represented right here, but again, that's kind of the publisher's choice. Over here on the right side, as we saw earlier, all of these end in p's. So essentially, how do you use this? We'll kind of follow this by saying this is my first row, my first period, and these are all s's, so it's going to be 1s2. Right here is my second row. This is going to be my 2s2. This is going to be my second row. These are my p's. So all these are going to be my 2p's. 2p1, 2, 3, 4, 5, 6. Over here, right, you have the third row, and these are all s's. So far, they've all ended in s. This is going to be 3s1 and 3s2, and then 3p1, 2, 3, 4, 5, and 6 all the way across. And then keep it going. So after 3p, it's going to be 4s, which is exactly what you see right here with 4s1 and the 4s2. And this is where it gets a little tricky, where it doesn't quite follow the pattern, at least not quite as easy. You got to pay a little bit of attention. But since this is my 4s1 and 2, that's taken care of right here. Well, then I have to fill in my 3Ds, and that's all this in here. Now, again, without any context, it's kind of hard to sort of start this when you're doing this for the first time. But you have to remember that even though this section right here is in the 4th period, it actually belongs to the 3D orbitals, because again, it follows the diagonal rule. So remember, as a diagonal rule, it would be 4s and then 3d. And that's going to be 3d 1, 2, 3, all the way up to 3d 10 in this spot with zinc. And then you can continue on. After 3d, you go back to the 4p. So back to this little part right here. You're back to, again, the 1, 2, 3, 4th row, and you're in the p area. So this would be the 4p electrons. So 4p1, 4p2, 4p3 over here at 4p6. And keep this pattern going. After 4p6, is going to have the 5 S's, and then your 4 D's, and then your 5 P's. After 5 P's, you're going to have your 6 S, and then after your 6 S, we see the F's for the first time. Now again, according to how it looks, you would be, okay, let's keep this pattern going. You would think this is the next step. But don't forget, if you look at the actual atomic numbers here, you notice there's a big jump. Well, obviously, they don't just skip elements. They just simply relocated a lot of these elements down here on the bottom. So again, this should be your 6s1, 6s2, and then this right here will be your 4f1. And 4f1, 2, 3, 4, all the way across. And then once that's done, you pick that up right here. Once you're done with the 4f's, you go back to the 5d's. And notice again that there's 10 of them, exactly how you expect. So 5d10. And then 6p6, which again is on the 6th period again, so that works out. Right, so again, takes a little practice, but you'll get used to it. You have to know where the S's and the P's, and then where it picks up right here with the 3D's. And these again is the first time you see the F's, and that's going to be on the 4th energy level, so all these are my 4F's. Underneath here is going to be your 5F's. Okay. Also, let's go ahead and identify these. Since this section right here all ended with S's, well, we're going to call this my S block. Right here, all of these in this section right here ended in a D something, so 3D something, 4D something. This is my D block. I'm sure you can see where this is going. This section right here is my P block, and then down here is my F block. Right? So this helps us organize and identify electron configurations a lot easier. So one thing I want you to do, make sure you remember what all this means. There's actually some sort of interpretation of the electron configurations here. So with the electron configuration of chlorine, you notice you have these 5 terms. Well, let's make sure we understand what each of this means. So let's kind of separate each term here. I'm going to focus on just, let's say, this one right here in the middle. So let's focus on this section right here. Now, as a reminder, do not forget this. This 2 right here in front represents the energy level. This P represents, I'm sure the only thing that you can possibly represent in this context is the type of orbital. So we're talking about those dumbbell shapes. And then the 6 tells us essentially how many electrons have been assigned in this type of orbital. Notice again the 3p5s, that means I've assigned 5 electrons to my 3p set, and it's not going to be completely full. Right, we're still missing 1 for this to be full. That's all I wanted you to do. Alright, now for the sake of practice here, you can go ahead and take a look at these. Notice that you have a way a pattern anyway that you can use to identify where the electron configurations are. So I'll give you a moment, and we'll get started in just, if you want to pause here and try them out yourself, we'll get started on the answers in just a moment. Okay, so number 1, how many elements have electron configurations that end in 5p? Well, if you look back at the periodic table, you notice that there's essentially 6 blocks. So you know that there's going to be 6 elements that end in 5p. Does that mean that those are the only elements that have a 5p in it? No, but those are the ones that end in 5p. Number 2, what element corresponds to an electron configuration that ends in 3d6? Well, again, if you look at your periodic table, you would kind of look in this section here. So let me kind of go back. This is my 3ds, and my 1, 2, 3, 4, 5, 6 spot ends up being, again, our friend iron. 2p4 is actually, again, going to be looking at the second row. This is one of the ones where it matches up nicely. And this will be the element, I believe, sulfur. No, I lied. I'm sorry. It's oxygen. And then 5s1 is going to be rubidium. And then 5d3 is going to be the element tantalum, Ta. Last one right here, without writing out the electron configuration for iodine, will be the last term in this electron configuration. So by identifying its location on the periodic table, it's in the 5th row, the 5th period anyway. It's in the p block, and it is 1, 2, 3, 4, 5 spots over. So its last term will be 5p5. This is a great way for us to identify electron configurations quickly and easily. Condensed electron configurations are pretty straightforward. Just kind of get used to these as well. You're going to start off with a core and then continue assigning electrons from there. Kind of also notice a nice little joke here with our noble gases. Let's start off with nickel. All right, so if you look at nickel, what would be the noble gas core? Well, nickel is in the 3Ds. And essentially the noble gas that comes, that is at least completely filled up, or at least what it looks like, is going to end up being argon. So I'm going to write it out with a little bracket notation here with argon. what this means is that I know, because of the noble gas stability, that all the electrons, again, filled up to this point are going to have the electron configuration of what looks like argon. So everything up to a 3p6. And then we're going to pick up from there and move on. So after 3p6, it's going to we're going to pick up at potassium and calcium all the way up to nickel. So it's going to be 4s2 and then 3d, and then 3d C8. We'll pick up in the next video.